This is the review for another type of graphing. And this is different from the last one because on the last one we had the fraction. So you could definitely go check that out because that's a totally different type. That's the one with asymptotes. This does not have asymptotes. So let's just get right into this and figure out how to graph this. So just like the other one, our first step should be to actually in the other one, our first step was to do the pre-calc rules, but there's not a lot of pre-calc rules you can do for this. Pre-calc rules only apply to the asymptotes really, because we haven't learned any pre-calc rules for this. So first thing we're gonna do is find the first derivative. So we do, obviously this is a chain rule. Again, there's another video posted for chain rule if you need to go just be refreshed on when to do it and how to do it. So we're gonna multiply those two. We're gonna get 6/3. So I'm gonna erase that. That's 2 times whatever's in the parentheses. And then we got to raise the 2/3. So we got to do 2/3 minus 1. So we end up with -1/3. And then times what's in the parentheses. So it's going to be times 1, but that can get rid of because times 1 is just the same thing because times 1 is an identity. So now we have our first derivative. Oops, sorry, got rid of the bracket there. I always just like to go right for the second derivative just so it's right nice in a row. Then you don't have to worry about finding it later. It's all in your head. So we'll do the same thing. We'll do this times this. We'll do -2/3 times x plus 5, what's in the parentheses. And then we got to do -1/3 minus 1. So it's going to be -4/3. Okay. So now we have our first and second derivatives all nice and easy, quick, easy. And we can get right into our first and second derivative test. You'll notice that this process took probably like a minute to figure out the first and second derivatives. Meanwhile, if you watch the other video where it was the fraction, it was a long time because you had to use the quotient rule and then it was canceling out and trying to simplify and it got a whole mess. So that's why I'm looking to do this one tomorrow. I think it's more condensed, but again, as I said, the other one is easier to just check and make sure that you got it 100% right. One easy mistake could just go unnoticed in this one. So that's why it's just good to be able to double check. And that's why some people might lean towards using the other type for their test. So we're going to start with our first derivative test. Just give me a sec. Our first derivative test. And then let me just label this second derivative test. And for the love of God, put x and y's on your axes. It will be the easiest point to earn on the test. And I will be very disappointed if you do not put x and y on your axes because you will be disappointed in yourself. So we can just, did I erase a negative here? Yes, I did. That makes more sense. We can start with our first derivative test. So how do we find the first derivative is we got to set it equal to 0. So obviously when we set this equal to 0, we find that the only time that this equals 0 is when x equals -5. X equals -5. And the easy way of doing that is just seeing that how can I put this? That when x equals -5, this bracket, it becomes 2 times 0 raised to -1/3. That's the only time that this parentheses becomes 0. And then obviously when you have 0 being multiplied by something, it's going to end up being 0, the final answer. So we have our potential turning points here, right? So we see that we have our potential turning point at x equals -5. So we can do our first derivative test. We can test a number that's less than -5. So if we have, let's say, -6, we're going to end up with a negative number inside the bracket. So a negative number raised to Let me just rewrite this for simplicity. So if this is raised to the negative exponent, it's the same as it being in the denominator. So we are left with this. It's always good to rewrite it just so you can see it. So if we're plugging -6 in here, we get 2 times, let's see, -6 plus 5 equals -1. So we get -1 raised to 1/3. Obviously, since this is not even, right? If this was like 2/3, we know that this is going to end up positive, but because it's 1/3, we actually need to follow it through. We'll see with the second derivative that we can do that. So -1 raised to 1/3 is obviously going to be negative. So we got a positive divided by a negative. So it's going to come out negative. So we got negative decreasing. Okay, so then we can test anything bigger than -5. I like to always just test 0. It's easy, simple. So we get left with 2 over 0 plus 5, so 2 over 5 raised to 1/3. And then obviously that's going to be a positive over a positive. So this is going to be positive, increasing. So I look at this and I'm like, it's going from negative to positive. And we had a potential turning point at -5, right? But now we need to see, is that actually a turning point? All signs point to it being a turning point. So I'll list it right here, -5, and then when x equals -5, it's going to be 0. Okay, I'll list it there for now. We'll see in a minute that it's not going to work out. Just keep that in the back of your head. Normally, that would be a turning point. All signs point to it being a turning point, but we'll look at it just in a second. So we'll do our second derivative test. Set that equal to 0. When does that equal 0? We see that that equals 0 again when x equals -5. Huh, that's weird because -5 was a turning point. So how could it be a potential point of inflection if it was also a turning point? Weird. We'll look back into that in a minute. So we'll do our second derivative test. We'll do something on the left of -5. So let's just say -6. If we have -2/3 times that. Oh, so let me just go through this in our second derivative test. And this is what I mean by the shortcut, where if it's raised to a even number, this can be rewritten as -2 over 3 times x plus 5 4/3. And if you don't understand that, I urge you to learn how fractions and exponents work right now, because it will really help you in the future. Remember that if this exponent's negative, it can be the same thing, just brought down to the denominator. And then obviously this stays in the numerator. That's already in the denominator. So it all works out. Okay. So if we have -6, we end up with 3 times -1 raised to the 4/3. And then that's under -2. So if you remember the rule that I said, if the top number is even, so obviously 4 is an even number, 2, 4, 6, 8, 10, 12 is even, the result will always be a positive. And let me just, I'll write this out long ways for you. That's the equivalent of writing the cube root of -1 all raised to the 4th. Cube root of -1 is just going to be -1. So you end up being left with -1 to the 4th. And then -1 to the 4th is just 1, right? -1 times -1 times -1 times -1. That equals 4, right? Because these equal 1, these equal 1, and then 1 times 1 equals 1. Okay? Just in case you were curious how it works. If you see an even number in the numerator of your exponent, it's going to be a positive result. So we end up with 3 times 1. So we get -2 over 3. So obviously that's a negative. Decreasing. Sorry, not decreasing, because this is our second derivative test. So it's going to be down. Right? And then we can go to anything above -5. So I like to plug in 0. It's just simple, makes our math easy because 0 just cancels out right away. So we end up with -2 over 3 times 5 raised to the 4/3. Obviously, we're going to be left with a positive on the bottom again, so we get left with a negative over positive. So we get negative again down. So that's interesting. I want to go back to the point again that -5 is both a turning point and a potential point of inflection. We see that it's not actually a point of inflection because it doesn't go from positive to negative or negative to positive. So our potential points of inflection, there are no actual points of inflection. So now I look at this and I'm trying to wonder what this graph looks like. And there's one big thing that I have not mentioned. When you have something that is a turning point, right, and a potential point of inflection, it's really a pond in disguise. So -5 is really a pond. So that means that there are no turning points. Put a big fat X through this because it can't be a turning point if it's a pond. And there are no points of inflection because, again, it's a pond. So we can go right to graphing this. We know that there's a pond at 5, 0, right? 5, 0 is our pond. Just let me look at something real quick. 5, 0 is our pond. We see that just one second. Sorry. Before I actually graph this, I want to write the intervals of increase, decrease, because it's always a great thing to do. Increase are going to be from -5 to infinity. And you're probably asking yourself, why didn't I include the -5? Well, remember we said that -5 is a pond, and ponds are always a soft bracket. If you want to memorize one rule for tomorrow, ponds are always soft bracket. There you go. And then decrease is going to be from -infinity to -5. Again, it's a pond. I'm getting those numbers, by the way, from up here in our first derivative test. That's increase, decrease. And then I'm going to do up will be from, no, there is no up because obviously it's all negative in our second derivative test. So down will be from -infinity to 5. Soft bracket again because it's a pond, in union with -5. Sorry, that should be a -5. -5 to infinity. Okay, and you can't include 5 in this because it's a pond. So you don't know which way. It's weird. Just don't include the 5. Don't include a pond ever. Don't include a pond ever. Okay. So now we can get to graphing. We know that we have a point at -5, 0. That's our pond. So now we can look to the left of that point. We have -5, 0. Now we can look to the left of that point. We have negative downward slope. So we have a negative slope, and we know that it's concave down. So it's going to look something like that. So then to the right of -5, we have a positive with a concave down slope. It's going to look something like that. And I hope that just by looking at this graph, you can tell more so that this is a pond rather than like a turning point or a point of inflection or anything like that, because you see that it comes like this. You see that sharp point. Anytime you have a sharp point, here's the rules for ponds. Sharp points, pond. Asymptote, pond. Vertical line. So if I have like a graph that goes like this, that's going to be a pond. Because if you took the slope, remember a pond is a point of non-differentiation. So for it to be a point of non-differentiation, you can't find the derivative of it, right? That's what differentiation means, finding the derivative. You can't find the derivative of it. So how do you find the derivative of something that's horizontal? Well, what's the slope of this line? If I asked you what the slope of that line is, it would be undefined, right? That's really sloppy handwriting. Oh my gosh, I am so sorry. It would be undefined. And that's the whole reason why you can't do it for a vertical line. So in my opinion, this is a lot easier than the one that has the fractions where you're just trying to go through it. let me just double check everything that it's all good. Again, you're not gonna have your calculator tomorrow, so you need to be confident in your math skills. You can always go back and plug in just to double check if you made a mistake, or you can, if you have enough time, you can even run through the arithmetic one more time. There's another video up that shows the graphing techniques just for a regular polynomial. I think it's been up for the last day. And then obviously I posted one that has the steps for the division, and that should be it. Actually, there's another type of question that I want to address before and that is, you know what? I will make another video to address that just so this one's not too long. Okay, that's it. The biggest thing is just knowing that if it's a turning point and if it's a potential turning point and a potential pond, potential point of inflection, it's going to be a pond. And that's just the big trick to this question. So you follow it down. It's nice to have these all in line because you just follow it right down. There's our point, -5, boom. And then the graphs just follow what you did in the tests. You can always double check them too. Obviously, if it came out something like this, that would be if this was positive, right? Then that would be up. But obviously ours was not positive, so that's why it looks like that. But that's how you get the shark fin, just in case you're wondering. So I'm going to close this video out. Yeah, you can always go back and just double check the work if you're unsure of anything. So besides that, that's really it for these types of questions. So I hope you understand it all. And I'm going to go through in my next and final video just how to do it without being given the equation. And I'll explain that more in the next video. All right, good luck.